Cool. So my talk is ambitiously titled Science of Deep Learning. Now, this is a bit of a bait and switch because I don't actually know that we have a science of deep learning. So instead, I'm going to talk about why we should have one, what it would look like if we did, and present a couple of case studies of trying to have a science of deep learning. Shout out to Rohin Shah, who leads the alignment team at DeepMind. A lot of the ideas here are quite heavily inspired by discussions with him. Cool. I guess some housekeeping stuff. So I'm going to try and end the talk on time, but I will be available afterwards for questions. I'm also going to try and make this talk a bit interactive, since it's the afternoon and you've all stuffed yourselves with food and drink. And so feel free to interrupt me at any point if anything seems confusing or you have a question. If there's too many questions, which I kind of expect there will be, we'll defer them to later. All right. Cool. So, yes, click. Here's a list of things that I'm going to talk about. So the talk is broadly structured into 3 parts. I'll first give a high-level overview of what I mean by the science of deep learning and some motivations. I'll then zoom into a project that Rohin and I and a few other colleagues did on understanding Grokking, which is, I claim, one of these confusing phenomena in deep learning. And finally, I'll come back to some high-level thoughts about how this could affect the future. OK, so out of the many confusing phenomena in deep learning, I'll start with 2 examples. So the first one is deep double descent. Just a show of hands, how many people have heard of this term? And how many people understand why it happens? OK, cool. I would not put my hand up on that question. OK, so to give a kind of overview of what this is, so I guess that in kind of classical statistical learning theory, there's this idea that you have a bias-variance trade-off. As you increase the capacity of your model, your sort of loss, your empirical loss on the training set goes down, but on the test set, at some point, your model, will, as you increase its capacity, will start to overfit the training set. And so the purple line goes up. And that's the initial bit of this classical regime in this diagram. But then a number of people, through various papers, have noticed that as you increase the capacity of models even further, you see this second dip in test loss, where it seems like increasing the capacity then reverses the trend. And despite the training loss being very close to 0, or in many cases basically 0, the test loss once again starts to fall. And in many cases, the test loss falls beyond what the initial early stopping regime was. Let me just stop there and check that this explanation makes sense for what deep double descent is, and check if anyone has any questions about it. Yeah. Sure. So I won't go into it too much in this talk, but I think basically what I want to point out here is that the kind of classical understanding is that when you increase the capacity, you're kind of increasing the ability of the model to overfit on the training set. That's basically what I want to point out here. Any other questions on this? Yep.
Is this always observed in training? And when is it observed, or when is it not observed?
Yeah. So I think It kind of depends on what you mean by always. For a long time, people believed in the classical regime, and this was because that was the only thing that they were observing. And it took a while for people to find the counterexamples. And often this happens because you actually need to increase the capacity quite a lot, or you need to train way beyond the kind of early stopping point to observe these kind of phenomena. And so it's not surprising that in many cases people just didn't see it. But like once the phenomenon was observed, there were like a number of papers. I guess the one I'm pointing to here is from Preetham Nakaran in 2019, where they showed, this was like from OpenAI, where they showed on a number of different like tasks and kind of deep learning architectures, this phenomenon can be seen. Okay, I will go on. Yeah. So the first puzzle is what's going on with deep double descent. What sort of model would explain why increasing the capacity kind of causes test loss to increase and then reverse trend? So here's another figure that shows that this is quite a deep phenomenon. So it doesn't just occur, or you can. It works for many different notions of model capacity. So you can, if you take a fixed point on the x-axis here, that's like a fixed model width. And then if you look at how it's varying along the y-axis, that's the number of training epochs. And the colors are indicating the loss. So if you take a fixed width, like 30, you can kind of see that the loss rises, then falls, then rises, then falls. And so that's going to produce the same kind of shape that you see here. Also, if you take a fixed point during training, so you take a fixed point on the y-axis, then as you vary the capacity of the model, as you vary its width, you also see the same trend. And in fact, in this paper, they also showed that this holds for data set size, even if you hold these two axes fixed. So that's like a third notion of capacity. So that's quite an interesting and weird puzzle, according to me. And yeah, there's this quote from this paper that there's this kind of term that's used in a lot of papers which are like trying to point at this confusion, which is like the implicit bias of SGD leads to generalizing models. So like past the interpolation threshold, once the models are like in the overparameterized regime or the overcapacity regime, you end up with like lower test loss. So that's one way of characterizing a well-generalizing model. And we don't really understand why this happens. Here's the second puzzle. Put your hand up if you've heard of intrinsic dimension. Okay, fewer people. So intrinsic dimension is this like really wacky thing. So probably a lot of people here have heard of LoRa or LoRa fine-tuning. And LoRa kind of relies on this idea that you can take a trained model and then you can make updates to it, which are in a much, much lower rank space. And that basically works. And this means that you need a lot fewer degrees of freedom than the full capacity of the model in order for it to learn. You can also do this, and in this paper, in the intrinsic dimension paper, they started with a random initialization, so randomly initialized model, and then you make extremely low rank updates to it. And it turns out that that basically works, in many cases, that works almost as well as using the full capacity of the model. So I think this is also a pretty weird thing. And empirically, it has a lot of success in the form of these low rank adapters. Yes?
About deep double
Sorry, maybe we'll come back to questions about deep double ascent later, just because I want to get through the rest of stuff. Unless it's a question about intrinsic dimension. Cool. Okay, so what do I mean by science of deep learning? I'm going to be ambitious here and put up a picture of the structure of scientific revolutions, which is, for anyone who's not read this, I would highly recommend it. It talks about paradigm shifts. In fact, it kind of popularized the term paradigm shift in science. And so what I mean is this kind of like Kuhn notion of science, which is to find models that will account for the observations, and then to notice when the existing paradigm is like failing to account for the like weird observations we're seeing. And in this case, I would point to the existing paradigm being statistical learning theory. And then like realizing that this is kind of a crisis in like a scientific sense. And trying to generate alternative hypotheses that will explain this observation. And I guess an example of this is the kind of many years and lots of like hand-wringing that it took to move from kind of geocentric to a heliocentric view of the solar system. Okay, so how do we do this science? I don't have a full answer, and I'm not going to be able to give you a full answer right here. But here's my stab at giving a kind of 2-minute answer. So I think doing this requires iterating between theory and practice in a way that's kind of rare when we're trying to explain these like modern deep learning puzzles. I guess I would summarize the steps as proposing a theory that explains some confusing phenomenon, then identifying predictions that this theory makes, devising experiments to test those predictions, and probably we'll find new anomalies. And this is progress. And then going back to step 1. And I would be really excited to see more papers that basically had this kind of structure in them. Oh yeah, and this was a pretty cool diagram, which maybe I'll take like 30 seconds to summarize. So this was made by J.J. Thomson in 1905, I think. And people might know this as the like plum pudding model of the atom, although apparently he didn't like that term. It was this idea that atoms are kind of enclosed in this uniform positive sphere. Electrons are enclosed in this uniform positive sphere. And he had this idea that electrons are like basically contribute to like the full mass of the atom. The positive stuff is like massless, and so there must be like, you know, huge numbers of electrons because he knew that they were very light. And this theory we now know is kind of very wrong, but at the time it was progress because it made some kind of strong falsifiable predictions. And one of the predictions, as people might probably know, and as is kind of appropriate for the Faculty of Nuclear Sciences, is like alpha ray scattering, which this model doesn't account for because you need something very heavy to scatter. Okay, so I guess we've gone on a kind of some sort of tour of science, but why is this important? So coming back to the alignment and safety case, the key hope is that understanding how neural networks work will help us understand how they generalize. This is important because by default, we're iterating quite fast on optimization methods, on architectures, on data sets. And by default, we don't really know what kind of program a learning process generates. And understanding the learning process helps us understand what classes of programs to expect. So here are some speculative success stories for what a successful science of deep learning agenda would look like. So one story is that it could boost mechanistic interpretability. So it could do this, for example, by finding that circuits have some property that mechinterp doesn't yet know about. And so you can use this property to look for circuits in a kind of automated fashion. It could help with the problem of eliciting latent knowledge. So I guess to summarize this problem, it's trying to know or trying to find out what the model knows about the world without relying on its outputs to tell you what it knows about the world. And so this would be a way to kind of automatically extract latent knowledge about the world from the model. And the way that science of deep learning could help with this is by finding, for example, consistency properties that would hold for predictive features inside models. And if you knew those consistency properties, then you could try to search for features using them. And that could, in some cases, that could help you distinguish between features that are like true knowledge versus features that are like something else. Another way that this could help is it could help you steer the learning process itself. So even if you, and this is like another way in which it's different from mechanistic interpretability, which is that you don't necessarily need to understand how the model exactly works in order to have some confidence that in order to like rule out like certain classes of programs that you might have gotten, or to like have some sharper expectation over what programs you might have gotten. Cool. I'll stop here in case there are any questions about this. Yes.
It's kind of a broader question, but on the like success stories, do you also see potential like failure stories where there's the project of the science of deep learning is successful, you have a great model of how deep learning works, but this like differentially boosts capabilities over safety, and it can be used by like less responsible labs to like build the.
Yeah. So I feel pretty sympathetic to this concern, and I think for a while I kind of held the position that probably if you're too successful at this kind of research, you should try to keep it secret, or you should not do it. I think lately I've come around more to the view that people are trying their hardest, basically, to boost capabilities. And I think I'm like skeptical that trying to adopt a more scientific approach is really going to like add additional options on the table beyond what existing capabilities efforts that are already trying to go as fast as possible would do. And I guess I see this more as like adding the option of like some sort of paradigm shift in our understanding of how these networks work. I think it's like a pretty like high risk research direction, and I'll talk a bit more about this later. But overall, I feel similarly about it as I do about mechanistic interpretability, which is that like understanding how the stuff that we're building works seems generally net good for being able to steer it, being able to avoid like dangerous situations. And yes, it has capabilities, externalities. I think that's probably worth it.
Related to this last piece and also the first point about boost McIntyre, if someone frames mechanistic interpretability as just one way of doing the science of deep learning, would you agree with that, or you don't conceptualize that?
I mean, so I don't want to plant any like terminology flags. Like I feel like if McIntyre people want to call their thing like science of deep learning, that's fine by me. And vice versa, I feel like a lot of science of deep learning stuff is going to look like using mechanistic interpretability techniques to like extract information about the model, to intervene on the model. Also, a lot of the progress will look like in inventing new McIntyre techniques. I think maybe mainly the distinction I want to draw is like you don't need a very like fine-grained reverse engineering the model into like fine-grained features and like fully understanding its behavior to like qualify as science of deep learning. And I think there's like many other things that are also useful.
But is there something that McInterpretability tries to do that science of deep learning isn't trying to do?
No, you could probably say it's contained inside science of deep learning. I want to focus more on the stuff that's not contained in it. Like I said, I'm not that interested in like where the intersection of these things is. Cool. Okay, so I will now talk about a case study, which is a project we did on trying to understand why grokking happens. Maybe a show of hands at this point. How many people know what grokking is? Okay, basically everybody. This is probably thanks to the great work that OpenAI did and also that Neil Nanda did in like reverse engineering grokking. So yeah, thanks to them. Cool, so this was work done at DeepMind by these wonderful people on the alignment team. Okay, so probably everybody knows this, so I'll speed through this a little bit, but grokking is a really weird deep learning phenomenon. When we started this project, it was even more mysterious because we didn't have the reverse engineered like circuit that these transformers learned. And we were kind of like, what is happening in this part? In particular, I want to kind of remind everybody about the deep state of confusion where you have something that has basically 0 training loss and like 100% training accuracy. And you keep training it, and for some reason, there's something in the learning process that is pushing the learned program away from something that already works basically perfectly to something else that generalizes. And I claim this is just really weird. So yeah, this is kind of the key question. Why does test accuracy go up even after achieving perfect training accuracy? Okay, so our work focused on this hypothesis of circuit efficiency. So what do I mean by this? Imagine you have a network that produces some logits. Let me just quickly check, does everyone understand logits? Or maybe like put your hand up if the word logit doesn't make sense. Okay, cool. So by logit, I mean the unnormalized output of a neural network that is trying to predict something. So it's the output before it goes into, before it turns into a probability distribution. Okay, so suppose that you can decompose this into a sum of 2 independent circuits that don't interact at all, except that their respective logits are summed together to produce the final logits. So this is clearly a pretty unrealistic picture of what happens inside a neural network. but that's good. Like I think like working with kind of simplified, unrealistic models to try and generate predictions is like what this whole thing is about. And then suppose also that sorry, it's just a bit confusing because I have two different clickers. All right. Yeah, suppose also that the red circuit uses fewer parameters to generate the same logits as the green circuit. So if you assume that all of the circuits have perfect accuracy, so if you assume that the logits are basically producing like perfect predictions, then you can improve loss by scaling the logits up by a constant to make the predictions even more confident. So we have these like we have this like cross entropy loss term when training this network, and we also have a weight decay loss term. And so cross entropy is pushing for scaling the logits up in order to reduce the loss even further, and weight decay is pushing for scaling the logits down because it requires weights to scale them. So yeah, so these two forces are in conflict, and in general, the thing you should expect from this is that there will be a preference for circuits that produce higher logits with a lower parameter norm. And so that's kind of our intuitive notion of efficiency, which is circuits that are able to produce higher logits with a lower parameter norm. Yeah, so in fact, in our paper, we proved this theorem that I won't go into here, which is that when you have different circuits with different types of different values of efficiency, then in some cases, these circuits will be weighted by their relative efficiency at producing logits. So we kind of end up with something that looks more like this picture, where you have lots of the efficient circuit and very little of the inefficient circuit. Now, you might be surprised at why there's any amount of the inefficient circuit at all. And the answer has to do with the way we implement weight decay. So if the way that the efficiency scales between them is like too slow, this is me like trying to paraphrase the theorem I showed earlier, then it's better for weight decay to kind of distribute parameters across multiple different circuits, essentially. So this is why you end up with like a small amount of less efficient circuit. So, okay, let me stop here for any questions. I realize I kind of sped through that. Yeah.
Hi, thanks. Are you considering possibilities of these two circuits also being mixed? Like maybe the generalizing circuit takes some part of the memorizations and uses them? Does that make sense?
Yeah, that definitely makes sense. So in this model, these are completely independent. So the only time they interact is when their logits add up. But I think like a pretty interesting extension to this is going to be like thinking about the kind of obvious competition for actual weights on which these circuits need to be implemented.
Do you see grokking at all if you don't put any weight decay? Or is it really caused by weight decay?
Yeah, that's another great question. So in this picture, I'm kind of hinting towards a story where weight decay is pretty important, and that's how we're defining efficiency. In fact, in some settings, you do see grokking without weight decay, but it happens kind of more rarely, and it's often slower, so it's a bit complicated. And I think you need like an expanded notion of efficiency to account for that stuff. Yeah. So for example, like the competition between circuits would be like maybe another factor that plays in there. Jan, you had a question?
Yeah, maybe just a comment. I sometimes like find it like pretty useful to think about it in terms of some sort of like basic economic metaphor, where you can think about the individual circuit as some sort of like small companies, like producing goods which is like predicting the logics. And if some of them have kind of like higher like fixed costs to produce the goods, so then they are kind of like gradually outcompeted, and you can imagine the whole system as some sort of like economy of small companies. And also you can extend it to like maybe if you have a circuit which is like already producing the predicted good, if you not know like predicting like closing brackets, it's maybe easier to build another company which will take or like predict like indirect speech and so on, so you can kind of import some like intuitions from econ. So that's my.
That's really interesting. Have you found any particular like economic model is like directly applicable in neural networks?
I haven't tried to make it like into like kind of like a formal model, more like an intuition around like why like people have a lot of intuitions like built for like how composition between things could be, and it's fundamentally it's a bit of an econ problem. Like you have kind of like a limited resource, like limited number of weights, like limited number of parameters, and ultimately kind of like any cognitive system like that needs to kind of has bounded resources, bounded cognitive capacities, and like solve some like econ problem, like how to allocate the problem resources to predictions like efficiently. So I think like there's a lot of overlap with econ.
Yeah.
If one econ friend who is like looking into more in something that it's
Nice.
out of the scope of this.
Yeah, that's pretty cool. Yeah, I totally agree that there's like lots of different notions of scarcity that you could try to analyze this through, and we've just picked like weights because weight decay is kind of easy. But just to give a couple of other examples, so you could have like robustness to noise is a form of scarcity, because you're kind of doing some form of gradient descent. There's going to be some kind of noise in there. You could even inject noise in there, and then there's like circuits that are kind of fitter are ones that are more robust to noise. Or a different notion of scarcity could be like bottleneck activations, which is a term from the circuits thread that Anthropic has worked on. And this is the idea that the residual stream has a lot lower dimensionality than like many of the other computations that are happening. And so stuff needs to like fit in there. And so circuits that are producing like things with smaller representations that fit into the residual stream might be fitter. So yeah, those are just like two more examples. Okay, I will carry on. Sorry to, but please ask me your questions later. Okay, so here's so far I've just claimed like this is more efficient, but why is it more efficient? So yeah, this is picture that each circuit is spending some amount of weight decay loss in order to buy some amount of cross entropy loss. It's a very very economic metaphor. And the generalizing circuit, like once it spends its weight decay loss, it doesn't need to spend any more because it can like predict the new examples. But the memorizing circuit does need to keep continuously spend weight decay in order to memorize each additional point. And so you can run these kinds of experiments, and this is like going back to like iterating between theory and experiment, which is like at this point we kind of felt like we had a sufficiently like concrete theory, and of course it wasn't like a simple picture like the way I'm presenting it here. We like did a bunch of other iteration as well, but you can imagine that at this point you have a kind of crisp theory, and now like what sort of experiments can you run to like falsify this? And so in this experiment, each dot is a kind of full, is the end result of a full training run. And the labels are random, so we're kind of forcing the network to like memorize. There's no like general pattern to learn here. And then we're measuring the parameter norm as well as the value of the correct logit. And the bars are kind of fixed data set size. So that's the color, which is like how many points did we ask it to memorize. And so you can plot these like, you can call them isologit curves, which are like for a fixed output logit, how much parameter norm was needed at various data set sizes. So how does the parameter norm scale with increasing data set size to produce the same logit? And this kind of very cleanly, or not very cleanly, but like fairly cleanly as these things go, supports the theory that the memorization circuit is like spending more parameter norm in order to produce the same logit as you increase data set size. So any guesses about what this same experiment should look for generalizing circuits? You can just shout out your guess.
Should be constant, I guess, the parameter norm, the right-hand side, like lines.
Yeah, great guess. And yeah, that's exactly the prediction we made. We were kind of, yeah, we were pretty like pleased when we saw this experiment result. And there's some subtleties here around like the initialization apparently mattering a lot. And so those are the bands, the colored bands that you see on the left. But if you kind of ignore some subtleties, then it looks pretty much like the way you'd predict. So then there's a separate question, which is that, okay, now we understand why gradient descent prefers the generalizing circuit. But still, for Grokking to happen, you also need this delayed phenomenon, right? Like the learning process is not just producing the generalizing circuit straight away. It first goes through the memorizing circuit. So what's up with that delay? Why does that happen? Yeah, so unfortunately, we don't really know. But this is like still quite good progress in my view, because it means that we've kind of isolated the next question to answer about Grokking. And another thing you can do often with these kind of questions is you can say like, okay, we don't know why this happens, but let's kind of assume some reason why it happens. And is that sufficient to explain the full phenomenon? And so we ran some like simulations using like this kind of multi-component hypothesis for why generalization happens slower than memorization, which I won't go into here. But yeah, if you use that, you can kind of recreate the phenomenon of Grokking in a toy setting. Okay, so time for some comprehension quiz. So the memorization circuit is becoming less efficient with more data points. The generalization circuit is constant. We also know that the memorization circuit is more efficient at like very tiny amounts of data. So this kind of implies that there should be a critical data set size where the two circuits have like roughly equal efficiency. So the first question is a warm-up question. So when your data set size is much lower than the critical data set size, what should our kind of training curve look like? Again, feel free to just shout out the answer. Sorry? Right, so does that look like, yeah, what does it look like if you just get the memorizing circuit in terms of train and test loss?
Your training is very good, and then your test loss never.
Yep, that's exactly right. So you just get like perfect training loss, test accuracy remains low forever. Okay, so now here's the real question. When you train on the critical data set size, what do you expect to happen? Sorry? You get both. All right, interesting. Any other guesses?
Okay. Depends how many epochs.
Depends on the epochs, okay. Any other guesses? Sorry? You get a sharp curve, but like where does it end? Is it like Grokking? Do you get like perfect test accuracy after some time? Halfway there, okay.
It would be funny if it alternated a little bit just because the plasticity.
Okay, it oscillates between the two.
Or 50% of
Yeah.
getting to one.
Yeah, halfway there. Jesse, do you have a prediction about what happens when you have both circuits?
The science, seeing both and see the distribution of Grokking times very widely.
Okay, yeah. Yeah, so I guess before we ran these experiments, we tried to ask ourselves, like, what does our theory actually say about what you should expect to happen? And actually, our theory says that two different things can happen. So you could either get like basically always the memorizing circuit, and then there's a flip, and then you just get the generalizing circuit. So that would kind of predict that you get Grokking. Or the other thing that could happen is you get a mix of the two. In our kind of toy theory, you would get a mix if the way that the efficiency scaled, as I was saying earlier, the way that the efficiency scale is like quite slow. And you'll have to like read the paper, ask me later for what I mean by this. But so we were kind of unsure, and in a way, this was a way for us to find out how the efficiencies do scale. Yeah.
Now I am a little bit confused what it means to predict something with your theory. Because shouldn't there be like one prediction?
Yeah, so I guess if we go back to this, unfortunately, our theory produced two cases. And so it's actually making two different predictions. And so it's not like fully constraining the predictions that you see.
Okay, so it's like a subset of Open's prediction.
Yeah.
Okay, great, thank you.
Can you say again what the two different?
So like either you get only one circuit, or you get a mix of the two circuits. But in particular, it's ruling out some predictions, like it's ruling out oscillating between the circuits, or like some other thing. Okay, so it's enough suspense.
But by either one, you mean either a memorization or generalization?
Yeah, that's right. Yeah, and what we actually saw was you do get a mix of two circuits, and you do get Grokking, but to partial test accuracy, which is super weird. And so this is a kind of like novel Grokking-related phenomenon that our theory successfully predicted. Or I guess depends on whether you want to count it as a success, but I feel like I will count it as a success. So here's another question. So supposing you have a fully grokked network. So this is a training run. The training loss has gone down, and the test loss has also gone down. So it's like fully grokked. And now we continue training on a new data set, or a subset of the data set that is much smaller than the critical data set size. So if you had started off training on the smaller data set, you would have never grokked. It was just too small. But now that you have a grok network and you continue training on it, what do you expect should happen? And yeah, any guesses? It should continue as a grok network. Okay, that's one guess. Sorry? It unlearns. And like in what way? Do you have a specific way in which it would unlearn?
Probably like opposite as Grokking looks like. So like steeply unlearns.
Okay, sharply unlearns. Yeah, any other predictions?
Ungrokks and rememorizes.
Okay, goes back to memorization, yeah. Gradually goes back to memorization.
It already paid the fixed cost of like Grokking. Why would it go back? The fixed cost has already been paid.
Yeah, okay. So
Stays grokked.
stays grokked, right. So I think all of these different answers are kind of pointing at like subtly different theories or like assumptions that you might have in your mind about how this phenomenon works. And it's kind of worth thinking about like what assumptions are being made for each of these guesses. So just as an example, if you had this kind of like random walk theory of Grokking, which is that you're kind of taking random walks in parameter space, and that's why it takes such a long time. Like, it's easy to find the memorizing solution because it's like very frequent in parameter space, and then you're kind of taking random walks in like unrelated dimensions, and eventually you stumble upon like a Grokking solution. This is a kind of like plausible theory for why Grokking happens and why it takes so long. But then this theory, I think, would predict that once you find the generalizing solution, you should kind of stay there, even if you reduce the dataset size. In fact, what we found looks like this. So this is on a log, the x-axis is on a log scale, so it's kind of hard to compare the speeds very directly. But I guess I would characterize this as slowly ungrokking. Yeah. And in particular, the test loss goes back to the point that it would be if you had started training on this data set. So it's like a way of saying that the starting point didn't matter. Yep.
You mentioned that you sometimes see grokking without weight decay.
Yep.
Do you see this happen without weight decay?
Yeah, there are setups in which you can see this happen without weight decay as well. Yeah. I think, yeah, I can't really say much more right now about it. Yeah.
A quick question.
Yeah.
So something that we alluded to earlier is that we think that memorizing circuits are faster and generalizing circuits are slower. And I'm wondering if you've seen whether when you do this experiment in both ways, you start in a Grokking state and you go memorizing versus memorizing, go Grokking, whether one happens faster than another, even if the circuit efficiencies are comparable. If that makes sense.
Yeah.
Maybe it goes back to memorizing way faster because for some reason that's an easier task or something like that.
Yeah, so I think basically in all cases it goes to memorization much faster than it will go to a generalizing circuit. Yeah, a kind of a thing we found was that in order to like characterize the behavior of like semi-grokked networks, or these like partial grokking networks, it often takes a really, really long time to like see semi-grokking. And this is because the data set size is like so small that it's just taking a really long time to find the generalizing circuit for some reason, for like whatever the reason is for grokking to be happening. And so a way we sped things up was we found semi-grok networks by taking fully grokked networks and then ungrokking them to the semi-grok point, which was much faster than like trying to go the other way.
Did you ever try similar experiments with not batching, but training on like global gradients, not stochastic gradient descent? I guess because I would expect much more smooth performance for all of this, and maybe you can like the transition much more.
Yeah, so I guess all of these experiments are with full batch training. Yeah, just
full batch training with the whole data set.
Yeah, it's a tiny data set. It's like 113 square or something. Cool. So, sorry. So I'm in the interest of time, I'm just going to like, how much time do I actually have left? Can I take 10 more minutes? If people want to leave, you know, feel free to.
Like we will just like directly switch to lightning talk, so like 10 minutes. There was no break scheduled after your
Okay.
talk, so like
Cool.
we are continuing the discussion.
Cool. Okay, so how does this connect back to like a theory of generalization, or like trying to figure out what sorts of programs we're learning? So I guess one of the core puzzles was why do overparameterized neural networks generalize? So given that they can memorize the training data, why are they learning these like nicely generalizing programs? And you could say that our work gestures at an answer to this, which is that because the memorizing circuits are less efficient, the kind of weight decay is preferring circuits that are simpler in the sense, or more efficient in the sense. And these circuits tend to generalize better because they don't need like additional weight norm for new points. And it seems plausible that a similar explanation could also apply to other regularization techniques like dropout. I think this is also pretty connected to double descent. So this is a nice paper by Xander Davies and David Kruger, and I'm forgetting the third person. They kind of, in this paper, they try to unify the kind of mechanisms behind both Grokking and double descent, and are sort of pointing to kind of similar set of ingredients that are happening in both. So you have a kind of faster to learn but less efficient circuit, and a slower to learn and more efficient circuit. And this kind of thing can also explain double descent. Okay. So yeah, we tried to do science of deep learning. How did it go? So I guess one important thing was like there was just a lot of tangents and a lot of like rabbit holes. So it was pretty important to focus on the central question. It's like kind of easy to say, but it's difficult to like actually form your hypothesis and actually like make the predictions before you run the experiments. It took a lot longer than we thought. By the time we were doing this project, Neil came out with the like fully reverse engineered like algorithm for what's going on in Grokking. Actually, one of the people on our paper, just for fun, I guess, tried to like hand implement a modular addition circuit in a transformer, and basically use the same algorithm that Neil happened to reverse engineer. So this was Janusz Kramer. So if you ever meet him, ask him about this. Also, this is it was less directly helpful for alignment than we had hoped, but maybe not less helpful than we had expected. By which I mean, I think this direction is in general going to look like pretty like high variance. It's going to look like doing a lot of like foundational puzzle solving, where it's unclear like how you can directly apply this to make a safer system. But yeah, the kind of broader hope is that solving these puzzles one by one is going to like lead to some kind of paradigm shift. Sorry, I'm going to now defer questions to the end, just for time. Okay, so I claim that there are lots of other confusing phenomena as well. So we talked a bit about intrinsic dimension. Distributional generalization is this weird thing where if you train a network with some percentage of errors in the training set, like 3% errors, for example, and then when you test it, it sort of appears to like mimic the error rate on the test set, which is pretty weird. Scaling laws, why are they so regular? What's actually driving them? The fact that increasing the number of like few-shot examples for like n-digit addition actually improves performance on addition is pretty weird, because you would kind of expect that with 5 examples, the model basically knows what the task is, and it shouldn't help that much to like go beyond that, but it does. We were talking about like deep double descent earlier. If in the kind of very over-parameterized regime, like all of the different models that could be represented are basically all achieving perfect training loss. So the model that ends up getting selected is kind of very heavily influenced by the prior of the optimization process. And so like how does the optimizer choice, for example, like Adam, or like whether or not you use momentum, how does that affect which programs you end up with? Okay, I claim that this is quite tractable because we can get a lot of information. So we have lots of ways to measure things. Compared to other naturalistic phenomena especially, we can intervene in very precise ways. This is similar to the story from Mecklenburg. Also, these confusing phenomena aren't like very inaccessible. You can kind of generate toy versions of them often with very little compute. So you have quite a fast feedback loop and you don't need much compute to do it. Another interesting thing is we kind of know the underlying laws. So unlike in, say, physics, we kind of know like basically what is driving the system. And so it's a kind of problem where you know both the bottom and the top, and you're trying to like understand the middle. Okay. Last bit. So how does this actually affect the future? So it seems relatively neglected, this direction to me. So most deep learning research is trying to make deep learning work better. And I guess on this point, I'm actually excited to go to the singular learning theory talk later and try to understand what that is. I think realistically, if timelines are pretty short, so if we're going to get like transformative AGI in like 5 years or less, probably we will manage to do this without really understanding why they work so well. And so maybe a lot of the like science of deep learning actually happens later through the AIs doing the research. Whereas if timelines are very long, then it feels like that would have happened because capabilities progress has slowed down for some reason. And so many of the people working on capabilities will kind of naturally turn to trying to understand how the AIs work. And so it feels like the most impactful world in which to do this research is kind of the middle world. And that seems at least plausible to me. All right, so key takeaways from this talk. I think doing better science of deep learning is like really interesting. It's impactful and neglected. It seems pretty tractable to me. And we actually tried it to understand Grokking. We made some progress. But it's pretty risky. And it might not matter very much if the timelines are short. That's it. Thank you.